So in this particular video, I'll go show you some direct methods to solve linear systems. In particular, I'll focus on Gauss elimination and Gauss-Jordan elimination, and their related topics of reduced row echelon form, the uniqueness of such, row equivalence, and finally I'll wrap up with an important result regarding homogeneous linear systems. When we solved systems before, we were looking for a certain target system, which was triangular form. We want the matrix equivalent of it. So a matrix is in row echelon form if it satisfies the following things: that all the rows that are entirely zero are at the bottom of the matrix, and in every non-zero row, the first non-zero entry, which we always call the row's leading entry, is in a column to the left of any leading entries below it. So for example, this matrix, this one, and that one, those are all matrices that are currently in row echelon form. All the rows that are entirely zero are at the bottom, and for any non-zero row, that leading entry for that row is in a column to the left of any leading entries below it. Now the word echelon comes from Latin. It means staircase. So you can kind of see why we say echelon because of these pictures. You can kind of see how it's like a staircase going downwards. This is just a way to define a system's triangular form, the form that we want in order to solve our systems. Now let's go describe a procedure, which we'll call row reduction, by which any matrix can be reduced to row echelon form. The permissible operations are called the row operations, and they just correspond to the operations that can be performed on a linear system of equations. We've already seen these, so I'll go through them quickly. The row operations that can be performed on a matrix are: you can swap the ith and jth rows, you can multiply the ith row by non-zero constant, and you can replace the ith row with the ith row plus c times the jth row. And I'm using the exact same notation that I did before with systems. So now let's detail the actual process of row reduction. Remember, row reduction is the process that we use to take a matrix and to, through row operations, reduce it to a matrix that's in row echelon form. So, in general, we work really left to right, column by column, and we work top down on that column. We work step by step on the rows that are currently not in the right form. Just repeat these steps while there is a non-zero row. First, focus on the leftmost non-zero column. That column now will be a column of leading entries. Just pick one. Any of them will work. Just pick a leading entry. Also, if that leading entry is not 1, consider multiplying that entire row by some constant so the leading entry is 1. It's just convenient to do so. But only do this if you don't introduce fractions, because you don't want to handle fractions from here on out. Now, move that row that has your chosen leading entry to the top of the current rows that we're working with by just swapping rows. Then, using this leading entry, which we'll now call pivot, just create zeros below it by using row operations. This phase of the process is just called pivoting. From here on out now, just ignore this row in all further iterations of this process. Pretend like it's not there, and neither is any entry in that row. So let's use the process of row reduction to perform a sequence of row operations on this matrix to row reduce it to a matrix that's in row echelon form. First thing is, look at the very first column. In that column, notice we have a whole bunch of leading entries. Pick any one of them. I'm going to pick the second one. The reason is, in the second row, see how every entry there is a multiple of 2? So then I can do the extra step of dividing that second row by 2 to make sure that my leading entry is a 1. Now I'll swap rows, in this case with the first and the second, so that my leading entry is at the top of the rows that I'm considering. Next, I will use row operations to get zeros underneath that 1. In this case, you take a multiple of the first row and add to the second and the third. I'll do it all at once, just this sequence, and that would then introduce zeros underneath my leading 1. All right, that's one iteration. Now, No longer look at that first row. You're never allowed to look at it. Just ignore it entirely. Now imagine there's a line there. And then on the remaining rows, work left to right to find the first non-zero row. The first non-zero column. Once you have this non-zero column, that will be a bunch of leading entries. Just pick one. In this case, I don't care. They both are fine. I'll pick the middle row, the second row of the overall matrix. Notice though that I could divide by 3 all the way through, but I'm going to choose not to. The reason is that would introduce fractions, and I don't want to work with fractions if I don't have to. Instead, I'll notice that I can just take the third row minus the second row, and I'll get zeros underneath my leading entry. Now that I've done that, I'll now ignore this row that has this newly formed leading entry and work on the rest. Again, working left to right, I eventually find the first non-zero column. That column is only the number 3. That's already a leading entry. There's no way to get zeros underneath it. And that's it. I have literally ran out of rows. So, if you follow these steps, you take the original matrix and through row reduction, you row reduce it to a matrix that's in row echelon form. So when row reduction is applied to an augmented matrix of a linear system, the resulting equivalence system can be then solved by using just back substitution. The overall process then is called Gauss elimination. So here's the basic steps. First, write your system as an augmented matrix for that linear system. Then use the elementary row operations to convert the augmented matrix to row echelon form using row reduction. Finally, go back to the original system with the variables, write down the equations, and then use back substitution to solve the equivalent system. So let's just use this process at least once. I'm going to use Gauss elimination to solve this linear system. I've actually already done so. I did in a previous video. I'm just going to show you that what I did before was actually Gauss elimination. First step, just convert it into an augmented matrix, and then go through the process of row reduction to reduce this via the elementary row operations to a echelon form. So here, notice that in the first column, the very first row, already is a leading entry. So I'll just go through the process by using row operations of introducing zeros beneath that leading entry. Then I ignore that first row. I look columns left to right. And I notice in the second column that in the second row, 1 already is a leading entry. So I'll get zeros beneath it. And once I've done so, this now is in a row echelon form. So I'll convert this from here back to its equivalent system. I notice that the last row corresponds to the equation 0 equals 0, so I ignore it entirely. That means z is a corresponds to a free variable, while x and y are leading variables. I'll say that z, being a free variable, is just some parameter t, and I'll solve the leading variables in terms of the free variable by using back substitution. Once I have that, I write the answer in column form. And that's it. That's how to solve that problem. Now there is something you should notice, that at the very, very end when you're using this process, the very last row is going to be a real hint as far as whether there is a solution at all or not. If your last row does not have a leading entry in the constant column, it must be consistent. There will be an answer. I don't know how many answers, because if there's a free variable, there's an infinite number. But as long as there's no leading entry in the last column, then there will be a solution, and the system was called consistent. For example, here, this would be an inconsistent system, because the very last row, if you turn it back into an equation, would be 0 equals 1. And that's impossible. So then it's pretty obvious once you get down to a row echelon form whether the corresponding system is consistent or not. Okay, so we now have a general way to go about solving linear systems. The process is called Gauss elimination, row reduction followed by back substitution. We want to improve on this. So for example, when can we say without a doubt that the systems are equivalent without actually writing down the entire solution? And then also, is there a way for us to improve our method to solve systems? And we can answer these two questions pretty quickly. To do that though, we need some more definitions. So we're going to say that two matrices A and B are called row equivalent. We'll write that as A tilde B. If and only if there's a sequence of row operations that converts matrix A to matrix B, and we'll write that as A arrow B. Now, hopefully it seems reasonable to you that every single row operation is reversible. That you can go from a matrix, do one row operation to get to a new matrix, and then use sort of the inverse row operation to go back. You just use the exact same row operation, but sort of like its inverse version. So if you swap two rows, I and j, you can then just swap them back, and you're right back to the original matrix. If you take a multiple of a row, you could then take that resulting matrix and multiply it by the inverse of that multiple to go right back to where you were. And if you take the ith row and replace it with k times the jth row, take that new matrix, now take its ith row and subtract k times the jth row, you're actually right back to where you were because you added a multiple and subtracted the same multiple. So you're right back to where you were. So, as an important theorem, two matrices are row equivalent if and only if they can be row reduced to the exact same row echelon form. To see why, we definitely need to explain it with a proof, so I'll go through it slowly. There's two things to prove. Suppose that two matrices A and B are row equivalent. Then just, if that's true, just further row operations will then reduce B, and therefore A, to the exact same row echelon form. If, on the other hand, they're both row equivalent to the same thing, the same row echelon form, then there has to be row operations that reduce A to R and B to R. But the row operations are reversible. So if there's row operations to reduce B to R, then there's row operations to reduce R to B. You could then use this sequence. Use the sequence of row operations to take A to R and then R to B to show that there is a sequence of row operations that reduces A to B. And that's the final result. So doing things in general and not using specifics can be hard for students to follow. But if it's true in general, you could then use the specifics as an example to further cement the basic concepts. So for example, I want to go and show you that A and B are row equivalent. Basically what the proof said is that if you row reduce B through a sequence of row operations to a row echelon form, and then take the matrix A, and you happen to row reduce it to the same row echelon form, then A and B have to be row equivalent because there's a sequence of row operations to go from A to B. To see why, remember in the proof, there are row operations to go from B to R. You can reverse them all. So here's me just reversing them all, going backwards. And then if you just take the row operations from A to B, just follow the arrows in this order, that is a sequence of row operations that reduces A to B. So A is row equivalent to B. So you might notice in my last example, there's actually a small problem. And that is, I got lucky, didn't I, that I row reduced A and B to just so happen to be the exact same row echelon form? Well, no I didn't, because actually that matrix that I row reduced A and B to happened to be what's called a reduced row echelon form, a special type of row echelon form. And this particular form is also really convenient to use to solve systems with. So, a matrix is called in reduced row echelon form if it satisfies the following. So first, it has to be row echelon form. But then, all the leading entries can't be just anything. They have to be 1, and all the entries above the leading entries is also 0. So, for example, these two matrices you see here, neither of them are reduced row echelon form. In matrix A, in the second row, the leading entry is not 1. In matrix B, the second row's leading entry is a 1, but the entry above it is -1. It has to be 0. So those two matrices are both row echelon form, but they're not reduced row echelon form. On the other hand, C here, that is reduced row echelon form. Now that we have this new form, here is a improved version of Gauss elimination. It's essentially Gauss elimination where we just skip the back substitution phase. First, write the augmented matrix for the linear system. Second, use row operations to convert the augmented matrix to row echelon form using row reduction. Normally now, for Gauss elimination, we would go right from here to the system and use back substitution. We're going to skip that step. Instead, now working right to left, bottom to top, use the elementary row operations so that the leading entries equal 1 and to create zeros above them. Notice that to do this, you never actually have to swap rows ever. You only use the other two row operations. So in this process, the position of the leading entries never change. Lastly, if the resulting linear system is consistent, convert it back to an equivalent linear system and then solve it by using leading variables in terms of the free variables. Just use parameters for those free variables. So I think it's a time that we look at another example. Here's a particular linear system. Now I've made it really simple so you get the basic idea quickly. To solve this, the first step is to just go ahead and write it as an augmented matrix, and then we row reduce it in order to get a row echelon form. So that's that. That's really easy, one step. Now normally for Gauss elimination, we then immediately go from here to the equation form and solve it by back substitution. We're just not going to do that yet. Instead, working from bottom to top, right to left, we're going to take every single leading entry, make sure it's 1, and introduce zeros above it by using row operations. In this case, in the second row, there is a leading entry of 1, but the entry above it is -1. So I'll go take the first row and add to it the second row, and that then gives me a new matrix who has a 0 above all its leading entries. And all the leading entries are 1, and that matrix is in row echelon form. So overall, that matrix is called reduced row echelon form. That was the goal of that step. It's essentially using back substitution, but not using the variables. That's why it's a little bit faster. Lastly, we then go back to our system. We can see that we have two leading variables, w and y, and we have two free variables, x and z. So I'll say x is s and z is t, and I'll solve our leading variables in terms of our free variables, and finally come back and just write out the solution in terms of a vector, w, x, y, and z. And then I just rip it apart in order to make it look nice. That's the answer. Okay, so why do we care about reduced row echelon form? Well, the main reason is that if you take a matrix, they could have many row echelon forms that you could row reduce it to. So for example, these three matrices, they're actually all row equivalent. So you could row reduce one to any of the others. And yet these are all row echelon forms and they're all different. So this one matrix has at least 3 and actually an infinite number of row echelon forms. That's not terribly convenient. But every matrix has one, but only one, reduced row echelon form. It's like a fingerprint for that matrix. There's only one that has it. Now this particular theorem is one of those really important things. It has 3 different important consequences right after it, but it's really tedious to prove. So I'm not going to do it right now, and I may not ever do it. It's because it requires a certain argument form called induction to make it nice. I can do a hand-wavy argument later on, but certainly we'll wait till at least chapter 3 to even come back to this. But also there's some other things we need to discuss. And one is that saying, let's find the reduced row echelon form of the matrix is tedious. No one says it. Most mathematicians, in fact, kind of go, let's just find the RREF of the matrix. It's just faster to say so. And I'll probably say it from now on if I can. Also, you should notice that there is row reduction. That's a process. And then there's reduced row echelon form, which is a type of matrix. It's really unfortunate that the word row reduced is used one way and reduced row is used in another. Yeah, I'm sorry. Let's look at some consequences of the uniqueness of the RREF of a matrix. Since it's unique, that means that we can use an algorithm or a computer or a calculator in order to compute it. Now it is true though that there are certain computations in the future that we're going to have to use the row operations by hand. So it's an important skill to know how to do by hand anyway. But most of the time, that's completely unreasonable. Doing it by hand is crazy most of the time. We just want the reduced row echelon form. We don't care how we get it. So for that reason, please go online and try to find ways to do so on your calculator. There's ways on pretty much any Texas Instrument calculator, for example, to type in a matrix to do any of the row operations, or if you just want with a single command, find the reduced row echelon form. Now, as a second consequence, since it's unique, we know that two matrices are equivalent if they have the exact same row echelon form, but there's only one reduced row echelon form. So if you take two matrices and find their reduced row echelon form, and they're the same, then the matrices are row equivalent. As my previous example, we looked at these two matrices before and noticed they had the exact same reduced row echelon form. So those two matrices had to be row equivalent. And as a last example, since every single row echelon form is converted to a reduced row echelon form by never swapping rows, that means the locations of the leading entries never change. So the number of leading entries in any row echelon form is actually always the same. It's always a constant. Because of that, we can define what we call the rank of a matrix. So the rank of a matrix is just the number of non-zero rows, number of leading entries in a reduced row echelon form, or in any row echelon form. Now that you have the definition of rank, we could then use this to create the rank theorem that we'll hear a number of times in the course. For a consistent system, you can now start using the word free variable, because you can't say free variable unless there actually is answers. Also, though, the leading entries in the row echelon form directly correspond to the leading variables when you write down in equations. Because of that, you get the following. If you have any matrix, be the coefficient matrix of a linear system, if the system is consistent and there's n variables in the system, then of course the number of free variables plus the number of leading variables has to equal the number of variables, n. But we can go one step further, because the rank of the matrix, the rank of the coefficient matrix, is also equal to the number of leading variables. So just solving for the number of leading variables in this equation and calling it rank instead, you get the rank of the matrix. The rank of the coefficient matrix of a consistent system is equal to n minus the number of free variables. It's a nice little connection between the two ideas. Before we dive into just general applications, let's go and look at a particular type of linear system. It's called homogeneous. This is just a linear system where all the constants are zero. I just gave you an example here on the page. Now, the nice thing about homogeneous linear systems is they're instantly consistent, because they always have the solution that all the variables are zero. We call that the trivial solution. If, though, there are no free variables, then instantly that can be the only answer. But if there is a free variable, well, then that means that free variable can be anything you like, and there's an infinite number of solutions. This is nice because it means then that we now have one type of system that we know the type of solutions. Either you have no answer, one answer, or there's an infinite number. You can never have exactly two solutions to the homogeneous linear system. But there's another reason to learn it, and that is because, well, there's a certain criteria that if you look at a homogeneous linear system, that you automatically know that there's an infinite number of solutions, and therefore there is a non-trivial solution where all the variables need not be zero. And this goes like this. As long as the number of variables exceeds the number of equations in a homogeneous linear system, there's automatically an infinite number of answers. And the reason why it's really easy, because every homogeneous linear system is consistent, I can use the rank theorem. So the number of free variables is instantly equal to n minus the rank of the coefficient matrix. But the coefficient matrix, if you row reduce it, the number of leading entries is equal to the number of rows, but that is going to be less than the number of columns, because there's more variables than equations. So that means the rank of A is less than n, because n is the number of columns. So that means that the number of free variables is automatically more than 0. So there is an infinite number of solutions. This is a really nice little trick. Anytime you have a homogeneous linear system and you want to know, is there an infinite number of solutions? You're guaranteed there is, as long as the number of variables exceeds the number of equations. So let's try some quick applications of what we just did. For example, let's find the equation of the line that's the intersection of these two planes. Now you know those are the general equations of the planes. So we have to have a line in 3 space. We know that the equation of a line can be represented in a number of ways. The important for us is vector form. The vector x equals some point that corresponds to a point on the line, and then it's plus a parameter times a direction vector. So to do that, well, the intersection of the planes is just of the two planes is just the set of all solutions to these two equations. So we'll just solve the equations. To do that, I'll write it as an augmented matrix, and I row reduce it right away to get its row reduced echelon form. From here, we go back to our system, and then I notice that z is a free variable and x and y are our leading variables. So we'll say z is our free variable t, and x and y I'll solve in terms of that parameter. I'll then write it in vector form, and that's the equation of a line. That's literally the vector form of a line. Let's try another one. This time let's take 2 lines. So I have the vector p, q, u, and v. U and v are going to be direction vectors. P and q are going to be points on these lines. I want to know, do these 2 lines intersect, and if so, where? It's not difficult. We just kind of unpack what we know. So this is the vector form of one of the lines, just writing it in terms of a single component, a single vector. And here is the vector form of the second line, again just writing it as a single vector. Now if these 2 vectors intersect, if these 2 lines intersect, then there has to be a choice of parameter, t and s. So those 2 components, the first component of each vector, the second component of each vector, and the third component of each vector, they have to be the same because they have to meet at the same place. So that means that there must be an s and t, so all those equations are true. But if you just get all the variables to one side and all constants to the other, that means in that system there has to be consistent. So then if they intersect, that system is consistent. If they don't intersect, then that system's not consistent. Let's just solve the system. Now, we know how to do so. We just write it as an augmented matrix, row reduce it, put it back in the system, and then use either back substitution or take it all the way down to its RREF and solve it from there. In this case, though, you get only one answer, that t is 5/4 and s is 3/4. If you plug t is 5/4 into the first line, you'll get a point. And that point's the point, that's the intersection between these 2 lines. That's it. And I think that gives you enough information to go and solve various different linear systems by using our direct methods, either Gauss elimination or Gauss-Jordan elimination. Along the way, I also introduced row echelon form, reduced row echelon form. Why reduced row echelon form is so important? I also gave you the rank of a matrix and the homogeneous linear system and an easy way to go about solving it, or at least knowing if there's an answer besides the trivial solution.